Again, just kind of wanted to welcome y'all. As Annie mentioned, my name is Rob Alley. I'm an engineer with Elrod Engineering, and as a brief introduction, for those of you who aren't familiar with our company, we've been providing sign design and structural engineering since the early 1980s, and proud to be a longstanding member of the MSSA. So I'm excited about sharing with you a bit about the engineering side of your signage and architectural element world. We're going to spend about the next hour and give you what is hopefully going to be a helpful overview for what goes into sign engineering. My intention is not to make an engineer out of you, but in our experience, if you as a project manager have a good basic understanding of what goes into the design of a sign, you'll first have a smoother working relationship with your engineer. And secondly, you'll be able to better serve your client, which is what we all want. As Annie mentioned, this is the first of a two-part introduction to sign engineering. In 2 weeks, we'll address freestanding signage, including existing signs. Hopefully, as I mentioned, we'll have time for questions at the end, so let's dive in. As I mentioned, today, we're going to cover two things. What is sign engineering? And let's then focus in on some particulars of wall signs. In 2 weeks, we'll look at freestanding signage and then existing sign structures and their inspections. So what is sign engineering? The two main topics that I want to cover today are theory and practice. Basically, the theory, what's the engineering behind this? What drives the design? Things like the building code, the risk category, the exposure category, design loads that are applied to a sign. And then the practice side, especially how it applies to wall signs today, what information is needed by your engineer in order to come up with a good design for you? And then some of the specifics about what makes a good request for a project. One of the most important things is the building code. In many ways, the building code drives the design of the sign. In a sense, the code tells us what loads are applied to the sign and how they are applied. So it is city and state dependent, and so therefore it can vary extremely widely across the region. For example, in Texas, it ranges from the default statewide building code of 2003 to, actually, I need to update this slide. It's several cities in Texas have already adopted the 2021 building code. So you have anywhere from 2003 to 2021 within the same state, and sometimes even within a local region within a state. Other states have specific building codes. So again, for example, Texas, they just adopt the International Building Code. North Carolina, Florida, several northern states, they have a state-specific code, which may just adopt the IBC by reference, or in the case of Florida, is very particular to the state. And so, again, need to be aware of those kind of things. I always like to point out Disney World, they have their own, the Epcot building code, and that it's a fun document, well, fun for engineers. It's fun to get into because they have building codes for obviously signage, but things like roller coasters, castles, and other structures that you would find in the Magic Kingdom and probably would have never thought about. So why does the building code matter to you as a sign company? In a sense, or actually not in a sense, but a sign that you build for one location may not be properly designed for a nearby city. And we see this most in cities that are still on older building codes, 2009 and earlier, as opposed to a 2012 and later building code. Surprisingly, cities do not often view codes as backwardly compatible. So if you're working at for a national client and they've got multiple sites that are going in, you may go into, you're installing a sign in Nashville. The building code is 2018 in Nashville. And then if you install it in Laverne, Tennessee, which is a suburb of Nashville, they would be on an older building code. So I believe it's a 2012 building code. Laverne will not accept engineered drawings that are stamped for 2018. Even though the analysis doesn't change and the code as it replaces signage is essentially identical, it has to be specific to what the city requires. That's something that you, and in particular your engineer, to be aware of. But also, again, if you're working with a larger client who has a family of signs that are going out across a large area, it needs to be designed to be as flexible as possible. And so sometimes that takes some insight on the engineer or the design firm putting together that family of signs to know what goes where and what's the most versatile building code. When you do the install, if you get engineered drawings from your client saying this is for 2018 because they did it for a broad national area and the city there is 2012, it'll get, most likely it'll get kicked back and you won't be able to pull the permit till those drawings get updated. So that's an important thing to be aware of. So this is a table showing a little bit of the comparison between the building codes and then what's called the design loads. The American Society of Civil Engineers has put together some design manuals that undergird the building codes and, without getting too far into the weeds, tell how certain analyses are done. Excuse me. So a couple things to draw from this. One is you can see the building code updates on a roughly 3-year cycle. The design loads update on an approximately 5-year cycle. So there's a little bit of overlap and crossover there, but your engineer should be very familiar with this as to which loads need to be applied based on which code is applicable. That affects the analysis that they do. But for you as a sign company, why does this even really matter? As I mentioned, the design manual that ASCE puts out tells the engineer how to do the analysis. Frankly, just because something has stayed up in the past or has always been built a certain way doesn't necessarily mean that it is properly engineered. We'll talk about this a bit more a little bit later, but wind loading is a good example. Typically, a sign has to be designed to withstand a 115 miles per hour wind. Unless you've been walking around outside in a tornado or a hurricane, or if you've driven an unshielded motorcycle illegally fast, you've probably never actually been exposed to that much wind force and I have no concept personally what 150 mile an hour wind feels like if it's blowing in my face. That is what we need to design to. It doesn't matter if the normal wind in Nashville is a 20 mile an hour or a 10 or a 5 mile an hour. That's orders of magnitude less than what we have to design to. So just because something's been done a certain way and has never had a problem doesn't necessarily mean it's been properly engineered. Two other factors that have an important impact on design are the risk category and the exposure category. The risk category typically is ranked 1 through 4, and that basically describes how critical a structure is. Structure being defined as a building, a sign, or anything. Or put it another way, what are the consequences to human life in the event of a failure? There are 3 exposure categories that essentially describe the topography of the surrounding area and therefore how the wind load is applied to that particular location. As you can see, exposure categories B, C, and D. I get a kick out of the fact that there's no exposure A because the committee decided that heavily built up areas are basically too complicated to model and that you should either do a wind tunnel study on the specific building or just assume exposure B. This is literally what the building code says as far as the risk category. But what do you as a project manager need to know? This is a good summary right here. Signage is generally considered risk category 1 or 2. As you can see from this slide, risk category 1 are structures with low hazard uses. Risk category 2 is, to me, again, a little bit funny, anything that's not in any other group. So it's kind of risk category 2 is the default unless it's 1, 3, or 4. In general, most people would consider a small to medium-sized freestanding sign as risk category 1, though the local codes department might disagree. Large freestanding signs or medium-sized ones located near crowded areas should most likely be risk category 2. Any sign attached to a building is risk category 2 unless the building itself would be considered 3 or 4. So basically risk category 3 and risk category 4, those are critical facilities that need extra design for protection. Risk category 3, schools, stadiums, large area where large groups of people would be. Hotels are often risk category 3. Risk category 4 are critical infrastructure types of facilities. So if you've got a sign going on a hospital, it's probably going to be risk category 3 because a hospital would be risk category 3. If you're putting a sign at a nuclear plant, it's going to be risk category 4. So what about exposure categories? As mentioned before, the exposure category is a reflection of the topography in the surrounding built environment. Essentially, it's a measure of how rough the ground is. I like to use an analogy of whitewater rafting. And basically, the faster the water is when you're rafting, the more force it impacts. So anything that slows that down, so, you know, a good narrow channel that doesn't have any boulders in the bottom, that's going to be flowing fast. The more you build up the bottom with those boulders, the wider the channel is, the slower the speed is. So again, it's not a perfect analogy, but if you think of the fact that air actually is a fluid, anything that slows it down as it passes over the ground is going to impart less force. So I'm going to summarize for our discussion, but you can see from the slide literally what the description of exposure category C is. It's open terrain with scattered structures, typical suburban to maybe a built-up rural environment. This is the default. If you don't know anything more about a site, you have to assume that it's exposure C. Exposure B is a more built-up environment. So again, this is a much more developed suburban environment, a downtown environment. This is also considered exposure B. So you can see it's more built up. Those buildings, whether they're the subdivision with all the houses or a downtown area, that slows down the wind. And so the wind load is actually a little bit less. Exposure D actually increases the wind loads that are applied on a structure. Without getting too technical, it's a long area of at least 5,000 feet leading up to the sign that is flat. And so other than the coastlines, it's probably not very common, even though you would run into it, and we've run into it some around the Great Lakes and even along the Mississippi River. You have this long lead up, so the wind actually picks up speed and increases. One of the things I like about this photograph of Miami is that here you can see exposure categories B, C, and D all in one photograph. To the right, where the ocean is, you've got exposure D, just a long open area. In the center where the red is outlined, that's exposure B. So that's a downtown area, heavily built up. But then if you look in the left corner, upper and lower left corners, that's exposure category C, where it's less built up. So you've got all three of them in this area. Your engineer needs to be aware of this, because if you've got an install for a gas station right there along North Beach, along A1A, it's going to be exposure D, and therefore it's going to have higher wind loads that need to be considered for the design. So now we get into the analysis. What are the loads that are applied to a sign that your engineer needs to consider? So you've got dead load, wind load, snow load, and seismic loading. Those are the four primary classifications. Dead load is quite simply the weight of the structure. That is a permanent load that does not change. These other three are what are considered live loads. Those are variable loads, and they have to be considered. Wind load typically will be the controlling loading that's applied. It's the force that's applied to an object, in this case, a sign, due to the wind. And it can either be pushing against a sign, pulling on it, or both. Snow load is typically not going to be a factor unless your sign cabinet is especially wide and you get a lot of snow, or your project is a canopy or an awning. And this is actually, just as a side note, an area where we get, frankly, a lot of pushback from sign companies when they're installing canopies, because most of the time, snow loads are not considered by people when they design canopies. And depending on the configuration of a building, drifting can be a real factor. We're going to talk more about that in a little bit. Seismic loading is, unsurprisingly, due to earthquakes. Not that big of a deal in the South, even though there are a few areas outside of California and Illinois where it has to be considered. So the wind load, as I said, the main live load that typically controls the design of a structure is a force that's applied on the sign due to the wind. ASCE 7-16 is the most current design manual that tells us how to apply wind load to a sign structure. I'm going to hit some without going too far into the weeds, going to hit some highlights of the design from this latest manual that you might want to be aware of for context. Changes every time the design manual comes out. The wind loads are adjusted. In this latest version, mainly it was focused on inland areas, so the non-hurricane areas across the United States. Generally, you saw wind speeds decrease a little bit, and we'll give some examples, with the exception of coastline areas. And then in this case, risk category 4, so those essential critical structures, they have their own wind speed. Used to be that they combined wind speeds for risk category 3 and 4, but they've separated it out. The design manual does present wind speed maps, and I'll give some examples later. Those are based on actual data. So it's roughly a 50-year rolling set of data that's used to calculate and update the wind speed maps. Those do change because wind speeds are getting worse. And so those periodically do get updated and they get more accurate. So again, that's a reflection of why you've seen some of the wind speeds go down in interior areas. A little more detail, but there's some elevation factors that we can use for, because the air is thinner at higher elevations, the equations now recognize that. And there's some other things that factor in that make it a more accurate evaluation. So I mentioned wind speed maps. This is a comparison between, on the left, the 7-10 version of the wind speed maps, and on the right, the current or the most current 7-16 wind speed maps. And so it may be a little hard to look at the detail of this unless you're looking at a large screen, but I want to focus on the interior of the United States. On the left side of the map, pretty much everything is 115 miles an hour on the interior. But if you look at the right, much of the inland area, especially if you look through the Midwest, is 107 miles an hour. That may not sound like a lot, but that can make a difference in your design as to what size through bolts you need, what attachment methods and things like that. So kind of the way we view it, the lower the wind speed, the more efficient we can make your design. Note the gray areas that look like smudges, mostly in the West, even though you do see some along the Rocky Mountains and some up in the, I guess it's the Allegheny Mountains up in New England. Those are what are called special wind zones. Due to the topography, a local wind study has been conducted. And so just because on a wind speed map, you may look at that border between North Carolina and Tennessee, and say if you were doing a job in Cherokee, North Carolina, you might look at it and say, oh, well, it's going to be 105 miles an hour. There's actually a special wind study that has been done, which could show higher wind speeds. Another example would be outside of Denver in the, I believe it's in the Pikes Peak area. If you look at the map, it's 115 miles an hour, but a local wind study has been done. And so design wind speeds there are 130 miles an hour. Important to know. Again, typically those are mountainous areas. This is a table that compares some of the wind speeds. So when you have program clients, if you're working with them doing a standard install across a large area of the country, brand books may need to be updated. Just because the wind speed is specified and designed in one area, it may not necessarily be valid for another area. So that's a good thing to bring up to your program clients, those national or regional clients who have families of signs. I've got a table here comparing some cities and states as they have made the switch. And just to show you some of the differences, Nashville, where we are, the risk category 2. So this is for signs attached to a building. The wind speed has gone down from 115 to 105. Similar in Huntsville. Mobile, which is down on the Gulf Coast, didn't change. Again, consistent with the philosophy that ASCE had, that hurricane areas were left unchanged. Augusta dropped a little bit. Mexico Beach, I like to point this one out because they're on the Gulf Coast, a little bit lower than Mobile, where for houses, most commercial buildings, signs attached to those, your design wind speed is 133 miles an hour in both cases. Again, that's good, that's fine. But remember, this is a design wind speed. When Hurricane Michael came ashore a few years ago, it hit Mexico Beach at over 150 miles an hour. So just because something is designed to the building code doesn't necessarily mean it's adequate for what nature throws at the site. This is a map showing the United States and various snow loads that are applied. Again, I know there's all kinds of detail on this and it's going to be hard to read, but kind of think of it in terms of color gradient. The darker the color, the less the snow load. So as you get up to, not surprisingly, up in Minnesota in the light yellows and the greens, that's a much higher weight of snow that has to be considered at the site. As I mentioned, most people in the South, we don't think about a snow load and how it might be applicable, especially since it doesn't snow much and a sign doesn't typically have much of a flat area to capture snow. But what about awnings and canopies? Your project may include these, especially I've seen it a lot at fast food restaurants where they've got canopies around or covering up the order areas or the doors, things like that. Surprisingly, even in the South, snow load can be significant and can even control the design. Most of Tennessee is 10 pounds per square foot. So that second level of purple that you can see, that's 10 pounds per square foot. If you look south of there, slightly darker, that's 5 pounds per square foot. But in upper East Tennessee, you've got 15 pounds per square foot. So you've got this gradient that continues to go up. One of our big clients is located in Green Bay, Wisconsin. Snow load there is 40 pounds per square foot. You get up into Minnesota, it's around 60 pounds per square foot. We'll get into this a little bit more in the second part of the session, but this snow load is often what surprises our clients the most, especially when it comes to canopies and awnings, and where we may have to discuss things with our clients to help them understand why things are engineered the way they turn out that they are. This is a graphic representing seismic loads. Again, typically they don't come into play, but you can see just based on the color, how significant, this is a measure of how significant seismic reactions are. We're well aware of how active California is, that big red and brown area over there. But don't forget, in the fall of 2021, or excuse me, 2020, actually just a few weeks before I was giving one of these webinar presentations, there was a 5.1 magnitude earthquake on the Virginia-North Carolina border. And the New Madrid fault line, which is right there where Tennessee, Missouri, and Arkansas come together, that dark brown area is potentially the most significant fault zone in the United States. That's how Reelfoot Lake was formed. The earthquake could be felt in Philadelphia, and it is, especially in West Tennessee, you actually have to factor in seismic loading as part of your analysis for structures. All right, so let's get to the fun stuff, the signage. I'm going to give an overview of some different sign types and things that your engineer will hopefully be considering. Admittedly, I'm only going to touch the surface in this. And again, I'm not trying to make you an engineer. I'm just wanting to open the window a little bit so that you better understand some of the design factors underlying your sign project and how that impacts the design. A lot of people use different names for signs, so it's important to use the same definitions. First, what is a wall sign? To state the obvious, it is a sign that is connected to something else, typically a building, but there may be some variations. These are the most common phrases that we see used for signs on walls, which are probably familiar to all of y'all. Sometimes people use a fascia sign, describe it as a fascia sign. That is technically something that is flush to the wall, as opposed to something that is set off on a raceway or post or other that sits away from the sign, the wall. A blade sign projects perpendicular or at least at an angle away from the wall. A hanging sign, or sometimes people call it a bracket sign, looks like a blade, but it's got a rod coming out or support structure coming out, and then a sign that hangs down from it. So it's a variation of a blade sign. So I want to look at some common examples just with some pictures and make some comments along. Just some of these may be very familiar, some of these may be new to you, but just different types of wall signs. This is about as simple as it gets. This is a flush mounted, flat cutout of the Golden State Warriors logo. Super simple. As communicated to us from our client, the main issue here was that this had to be designed to withstand over exuberant fans from trying to take it home with them. Again, this is another simple example. Channel letters, and then that slash logo, letters mounted flush against the wall. Question to consider: what is the wall type? They've got a generic cross section down here that doesn't necessarily apply, but again, super straightforward, just channel letters. Gets a little bit more complicated when you've got letters standing upright on a raceway. So as you can see in the upper right, you've got the wall section, and then you've got a kind of a canopy slash raceway projecting out horizontally from the wall. And then you've got the letters going up. And then in this case, it's a little more complicated because the letters are going to have a tendency to rotate when the wind load is applied. So there's a moment there, or an overturning load, that has to be considered to make sure that the letters can withstand that, and the raceway and even those two bolts, through bolts connecting to the wall, have to be analyzed to make sure they can handle that. Here's an example of a blade sign, of a hanging blade sign. Remember, the blade sign is projecting out from the wall, and it can be, the sign can be fixed or it can be suspended. So in this case, you've got the sign, the little cabinet of the sign is actually fixed to the support member. This is a more complicated design than one that is hanging loosely, such as with chains or cable or however you want to attach it, that is allowed to just swing in the wind. Since this is fixed, more loading is applied to the support member, which can sometimes result in a seemingly oversized attachment method or even support member there than you would normally expect, but it's all because of the loadings that are applied. This wall sign is getting a good bit bigger. Overall height is about 66 feet. It's a sign that went into the Joe Louis Arena in Detroit. Always get a kick out of when the Nashville Predators go up there and beat up on the Red Wings. Doesn't happen a lot, but it does happen some. Again, technically this is a wall sign, but at over 66 feet tall with all the framing, the EMCs and display boards that go into it, and the people that are walking underneath, the connection details get very, very important. In this case, the original design of the building called for these large displays. So it was pre-designed, the structure was pre-designed to handle the display. But if you're involved in a project where you're retrofitting an existing building, those support connection details can get very complicated. You can see over there on the right side, the red horizontal stub outs. They're just representational in this drawing, but the building engineer had actually built those, and those were ready to go. We just didn't have the information yet at the time. Rooftop signs, technically not applied to a wall, but are within this family of signs. These types of signs, these roof signs, can impose very significant loads onto the roof of the structure that may not have been considered when the building engineer did the original design. It's really important, if you have a client asking you to get involved with this, to make sure that there is a building engineer who's involved in the project. Typically, a sign company like a sign engineer like us will limit our analysis to the loads that are applied to the roof. Because the building is just so complicated, we won't try to figure out if the building itself can handle it. It's just too complicated. You don't want to pay your engineer to analyze the whole structure and how the loads are distributed through it. So it's really important to have the building engineer involved as part of that so that they can approve the loading that is applied from the roof mounted sign structure to the roof itself. The sign engineer will be able to design the framing, but to make sure the roof can handle it, you need to make sure the building engineer is involved. This is an example of some different types of canopies. As you can see, there's a wide range of canopies and awnings, most of which are straightforward. Notice the middle picture though. When you have a deep rod hung or even cantilevered awning like this, snow loading and drifting can become the controlling issue. Depending on your wall type, in this case, again, all three of these are, looks like we've got stone, we've got brick, and then we've got some kind of another stone type surface. Those are good, but if you have an ephes wall, any bolts holding up the canopy are actually cantilevered out. It may only be 2 or 3 inches, but if you can envision an ephes surface on a wall, the ephes provides no structural support to that bolt. So it's sticking out 3 inches and is cantilevered by the weight of the canopy. That unsupported gap can be significant. It's a little bit esoteric, but again, the engineer needs to take that into account to make sure those bolts are sized properly. These are marquee signs. Again, just cool signs, neat, a variety of things that you may run into. Some of these were new signs. Some of these were refurbished, and you can get into all kinds of mounting conditions. The one in the middle, the Sanger Theater, that was a neat one because it was a really old building down in New Orleans. And at the time, they didn't even have construction drawings for the building because it was so old. And so a lot of exploratory work had to be done as to how the sign was actually going to be attached to the building itself. Another type of wall signage that people don't really think about is aerial identification signage. This seems to be becoming more popular with major sports venues. Even though these types of signs are applied and mounted to a roof, in this case, it's not paint. These are actually standoff letters. and logo, they're approached in a manner that is very similar to the wall sign, except that these are huge and they're lying flat, which are imposing all kinds of different stresses to the sign due to the orientation. It was a fascinating project that we got to work on because of these unusual design considerations. Over a 200 by 200 square foot area, you had all these different roof penetrations of the outriggers for the letters on a curved roof. So every sign, every outrigger had to be a different length because of the curvature of the roof. We had to consider the deflection of the actual face. Normally, when you think about a set of channel letters, if you've got acrylic faces, they're standing upright and they do fine because they're vertical. You lay it on its back and make it 20 feet long, they're actually going to deflect and sag. So how much deflection is going to happen? Is it too much such that it might break? Are you going to have to support them in different places? And if you do support these faces just at different points, what impact will that have on the lighting such that it causes shadowing, things like that? Another thing that we had to consider was physically, how did these letters get up to the roof? A crane could lift them part of the way, but it couldn't extend all the way out. So we had to come up with trolleys and different ways of actually physically getting the letters to where they were going to be installed. Really fun, really neat project. So reviewing some of these design loads, we've looked at the pictures, want to talk about this again just a little bit. Dead load, again, that's the weight of a sign. And in the case of a wall sign, that's going to apply shear and tension to the wall. So those connections are what's going to be considered. Pretty standard unless you've got an unusually deep sign or it's made out of unusual materials. So it may require some additional information for your engineer. The wind load, as I mentioned, it usually controls, but not always. A thing to mention with wind load is, and we ran into this just last week, just because the building code refers to a specific design manual. So say, for example, the 2021 International Building Code refers to the 7-16 design manual. There are wind load tables and charts in that design manual, which we looked at earlier. We were looking at a site in Texas, they're on the 2021 building code already. You look it up and by reference, it should be 105 miles per hour. Well, the city still requires 115 miles per hour. We also see this in different Florida cities where they've stuck to certain wind speeds that are different from what you would think. So these are just things that your engineer needs to know when they're doing that wind analysis. I mentioned a couple of times snow load, in that a lot of times you wouldn't think about it applying, but think about a deep canopy like that one that we showed, the rod hung canopy that was about a 4 or 5 foot projection out from the wall. You run into a situation, a case called drifting, whereas depending on the height of the wall and the depth of the canopy, snow builds up closer to the wall. And there's a formula that the design manual has for figuring that. Last year, we looked at a project in Las Vegas. They had an entryway canopy where you drive in and park under to unload your luggage. You wouldn't think about snow being an issue in Las Vegas, or at least I didn't. They actually do have a 5 pounds per square foot snow load, which is pretty typical for across the southern part of the United States. Due to the height of the hotel where this canopy attached to the wall, the snow loading actually built up to over 30 pounds per square foot right up next to the building. So you got 5 pounds per square foot out at the edge. And as it gets closer to the building, it increases to 6 times what the loading is out on the edge. That actually became significant enough that the internal framing for this canopy had to be redesigned to handle that additional load, because it just wasn't adequate. As I mentioned, this is typically where we get the most pushback from sign companies when we have to consider snow load, because a lot of times it doesn't make sense from just walking around outside that snow could be significant, but it really can. Seismic loading typically doesn't control, but it might. It's just something to be aware of. It's not as prevalent in the South unless you're over in West Tennessee, Eastern Arkansas, but there are things to be considered. And again, your engineer should be aware of this kind of stuff. I like to show this example. This is from just 13 months ago in Smyrna, Tennessee, where our office is. We had a pretty heavy snow. I think we got about 6 inches. And this is a canopy that was a rod hung canopy that was actually attached to the bricks instead of being connected to the block inside the wall. And as you can see, just peeled the brick right off. Not an unusually large snow, and it can have a pretty serious impact. So you always want to make sure that these things are well anchored and well designed. Another thing to remember is local building codes may have other issues, other things to consider beyond those design manual standards. We've recently run into 2 different sites that I like to bring out. One of our clients was looking at installing a location up in New England, and the local city had a point in their signage ordinance that did not allow signs with humans or animals images in the signs. Don't know why, but they just didn't want images of people or animals in it. Our client had a logo that had a human in it, and because the city would not allow a variance to it, they wound up going to another place. And the city lost a potentially really good member of the community because of that code. But had the building codes not been checked, had the signage codes not been checked early in the process, our client may have moved fairly far down that road and then had a problem with their signage. Another example that we're seeing lately become more common is sign ordinances not allowing a wall sign to project above the roof line of a building. And that's kind of a gray area when you have a parapet around a building. The codes may even require that the building have a parapet to hide any of the mechanical systems for the building, but excludes the building from having signage above the roof line, which is below the parapet. So again, just something to be aware of. If you do get involved for your clients in that code check part of the project, sometimes you have to dig a few levels deep to make sure there's not going to be some kind of prohibition against that. Getting a little bit into the weeds here, but things to be aware of to give you context of design. The location of a wall sign of a building can be significant as well. And so this is something that your engineer is going to consider as far as what loads are applied. This is a graphic straight out of the building code about a building. And what I want to point your attention is not so much the specific numbers, but if you see in the upper left, the 4 and the 5, zone 4 and zone 5. Zone 4 is kind of the middle of a wall. Zone 5 are on the edges. As you can see from the chart, there's a factor that's applied for zone 4 of about 1.1 in our equations. In zone 5, so near the corners and the edges of a building, it's a higher factor. So there's going to be more wind applied as you get to the edges of the building. This is an example of a parapet situation where basically you can see windward and leeward. These are the wind pushes and pulls on a sign. And so if it's down low below the parapet, you have one condition, this P5 condition. If you're up on a parapet, there's a P1 is a higher wind load that's pushing on the sign, and there's a P2 that sucks on the sign, even if it's on the other side of the parapet. So these were all done by the engineer in their wind load studies when they do their analysis, or it should be done. But sometimes you can see some surprising, we've seen if a sign is down lower on a building and then they have an identical sign higher up above a parapet or at a parapet, you can have significantly higher wind loads. And so just a different design for an identical sign, just in a different location of the building. Want to talk about some of the different wall types and mounting conditions and give you some examples of things that we see and approaches that we like to make with some of our drawings. This is a detail from a national sign program project that we have with a client. They wanted us to pre-engineer multiple attachment methods because they didn't necessarily know when they arrived at a site what type of building walls there might be. And so we came up with, in this case, 4 different types. They run into something that's an oddball case, we do a site-specific example, but these are all pre-engineered so that they know they can apply the signage to the site-specific location. Just kind of a way that we try to help out our clients with their design. Wanted to show this example as typical for brick walls. As I mentioned with the canopies, rarely do you get to just attach the sign to the brick unless it's really, really lightweight. So, you know, so maybe one of those face cut letters or something you might be able to apply directly to the brick without having to penetrate into the building. But actually, just a few weeks ago, we had a site in Nashville with some very light channel letters. The sign company thought they had gotten approval for mounting the letters to the brick from the permitting department, which we then engineered at their direction. And then when they submitted for permits, those were rejected. With the permission of the client, I spoke to the permitter. He acknowledged that mounting to the brick, just anchoring those letters directly into the brick, that it worked from an analysis point of view, but he didn't want to take a chance of the brick peeling off. And so we had to come up with a different, more secure mounting method, which an example, through bolts, anchoring further deep into the block, things like that. But just kind of recognizing that we're starting to see permitting departments get more strict about some of these things that in the past you could do, now not so much. And this, like I said, this is just a typical detail going in this case on the right in the blocking, just to make sure it stays up. So what information does your engineer need? You've got a project and you're ready to get them going on the engineering. Obviously, they need the dimensions of the sign. If there's anything unusual about the sign itself, the construction materials, weight could be a factor. We've got rules of thumb and typical values we use, but if something's unusual, we'll need to know that. It's helpful to know the way that the sign is going to be constructed. So the materials and the framing, things like that, so that we know how to attach the, if we're going to use lag screws to go into this wall, we want to make sure there's something on the inside of the sign cabinet or the letters to attach to. The information about the wall type. If you can get structural or architectural wall sections, that is wonderful. Sometimes on older buildings, you may not know, and so somebody may have to cut in and just kind of figure out the wall section. But again, your engineer needs to know what's being connected to so that they can properly specify that. Another thing which a lot of people don't think about mentioning to your engineer is, do you have a preference for how something's mounted? There may be a dozen different ways that we could engineer this so that it properly attaches. But unless you may have particular sizes, particular techniques that you just prefer to use, it helps us, your engineer, to know what those things are so that they can get it done best for you. Sometimes the sign has already been manufactured. Sometimes it's already been installed. So survey photos, those dimensions, fabrication details, those types of details are very helpful. This is an example of, I like to show this example from a client of ours. You've got an engineer that you like to work with. So how do you communicate that information? This client does a lot of repetitive signs with us. And so we came up with this order form that's got everything on it, and they just fill in the spreadsheet, everything calculates out, they send it to us. That way they know on the front end what their cost is going to be, and then we're able to acknowledge it and send it back. Really helpful when all that information is right there. The order form on the previous slide is actually attached to this email. And so I like to use this as an example because it's in a very condensed way. It contains a lot of information. There's a zip file that has a geotechnical report, artwork for the signs, building survey, photos, all that available information. In the middle, the street address. Lots of times that gets omitted, but we need to know the street and the city so that we can know the proper building code. And then down below, they've included what they know as far as specific code information that they've done from their code check. So again, that's helpful. This slide is an example of a checklist that we'd be happy to send you that summarizes most of the information that your engineer will need. Obviously, we can't capture every situation with the form, but it does get most of it. And typically, if you don't know all this information, your engineer can often make it work out. They may have to ask some questions, but more information is always better. I always like to mention if that was a good sign order, what's a bad sign order? There have been times we get an email from somebody and there's no address for the site. There's no contact information for the client other than the name, the email address, and there's no dimensions on the sign. Really makes it hard for us to come up with an estimate for you. Or the slightly more difficult, but sometimes more fun case of this is what we installed. Now the city is requiring us to get a permit after the fact. Can't you make it work out? I want to look at some examples of some drawings from a project that we did this week, drawings and calcs, and just point out a couple things that for you as a sign project manager to be aware of. I know we don't kid ourselves. We know there are times when you just need the engineering for permitting, and your local sub may not even actually look at the drawings when they do the actual installation. So I've circled a few things that in this case are worth paying attention to. We specify a typical spacing between attachment points. Evenly distributing the load. Does it have to be exactly 1 foot 9.5 inches on center? No, it can vary a little bit, but those are evenly distributing the load of the sign to the wall, and that's the way it should be applied. 3/8 inch A36 threaded rods in this case. Those are what the design was done to. The material properties of that, the loads were applied to it. That's the minimum that it takes to work. You can always upsize, you can always use better materials, but if you're going to deviate from it, get your engineer's approval to make sure that it's still going to work. Over on the right side, you can see the blocking there. If we show that blocking is necessary, blocking really needs to be there. If there's no way to get blocking into the wall, let your engineer know so that they can come up with a different method. Everything's based on certain assumptions, and so you don't want your engineer making a bad assumption. This actual site came about because our client had a local person do the install. They did it incorrectly. The permitter actually came out to the site, the inspector did, and I know that doesn't happen all the time, but they started looking at it and they said, you've installed it different than the engineering. We're not going to approve this unless you can get engineering to demonstrate that what you did actually works. And so we had to scramble and do that, and everything checked out fine. But we just needed to at the last minute, it was holding up their permit approval, and the ultimate client, the end user, was not happy about that. The next slide shows the calculations that went with the sign. A couple of things to point out. A lot of times I know you don't even necessarily look at this stuff, but just so that kind of educating y'all about what goes into it. If you're looking on the slide on the left, you see we summarize in that table the wind speed that was applied, the risk category, the exposure category. Good information to know, especially to double check that was right. You note the wind pressure, 69.7 pounds per square foot. That's what's being applied to the sign in this site at 175 miles per hour. Coastal area Florida, by codes, that's what it has to be. How often does 175 mile an hour actually happen? Not very often, but we had to do it. Lower right on that first left slide, you've got some properties for the 1 1/4 inch, or excuse me, 1/4 inch diameter bolts, and the number of fasteners. 30 is what it needed to be. You look in the middle, that's kind of a way to check. This is a printout from the actual wind analysis software that we use for every calculation, verifying you've got 175 miles an hour. We've got the height. All this stuff goes in to where on the third page, you see the pressures that are applied. Actually, I apologize, I circled the wrong one. But these are all the different design pressures that get applied, different zones for the sign. So in conclusion, hopefully this has explained a little bit about the fundamentals of sign engineering and what goes into your wall sign and what your engineer needs to know to give you a good design. As you can see, sign engineering can be relatively straightforward, but there's also a lot of complexity to it. If your engineer doesn't want to know this information that we've talked about, it may be time to reach out to somebody else. And there are several very good sign engineers out there that you can work with.